U2 and U1 and U2 because of dropping voltage. Okay, dropping voltage, and the K is the transformation ratio or transformation ratio, and for that, and now if we if we take the U1, okay, U1 divided by W1 is equal to U2 divided by W2 here, okay, and otherwise if we get, okay, if we get the expression, for example, if we take, so U1 is equal to U2 multiplied by the turn of the secondary winding, okay, W2 here divided by W1, okay. For example, in practice, if the U1 it changes, it's various, leading to the various of the voltage value of the secondary winding or U2 here, okay. And now how to give, okay, let me say again, and now have a look at this expression carefully, okay. In practice, of course, if you want to give the U2 as a constant, okay, if the U1 is various, the values of U1 is various, it means that we have to change the turn of the winding, okay. So either we can turn up the winding, we can change the turn of primary winding or the secondary winding, okay, according to you. So if we, let me come back to this one, I think it's better here, okay. And now if you look at this expression, you can see again from this one, okay, we can deduce, so U2, okay, is equal to U1 multiplied by ratio of W2 to W1 here, okay. And of course, as I said a few seconds ago, so if U1 it changes, and now if you want to give the values of U2 as a constant, okay, how to do, okay, how to do. Who know my questions? Okay, how to do? Who know my questions? Yes. So if there no answer, I would like to call in the list of the student. Bùi Mạnh Cường. Please answer my questions.
Can you repeat the question?
Yes, so have a look at, okay, so you can see the slide like this, okay. Have a look at this expression, okay, and now from this expression, okay, I deduce, okay, I transform from this one to that one, okay, that one with my mouse here. You can see, so U2 is equal to U1 multiplied by fraction like this, okay. So for example, if U1 it changes, and now if you want to give the U2 as a constant, how to do?
We change the ratio of W2 over W1.
Yes, I know, and everyone know, but and so either you can change the turn number of W2 or W1. Yes, we know we have to change the ratio of W2 to W1. Of course, you need to change the turn number of primary winding or the secondary winding. I mean,
we change the voltage.
You change the voltage, U1?
Or in U1 or U2?
Yes, I know. I mean that. If you look at normally at the home, okay, if you want to give, if you look at the Liwa transformer, okay, or if you look at the transformer, okay, you can see, for example, if the input voltage is various, okay, and now if you want to give the output voltage of the machine of the transformer as a constant to supply for the electric device at the home. Okay, of course, as you said before, we need to change the ratio of W2 to W1. Yes, I know, and everyone knows this way, but I would like to ask you, so either you can change the turn number, according to you, you can change the turn number of W2 or W1. Do you understand what I'm saying?
Let me think.
Who can answer my questions? It's very, because if you know well the theory, or otherwise know well theory, you understand very well. Okay, so if you can see this question is also so it will be also appear in the middle exam or the final exam, because they will ask you about that. Maybe I will. Yes, I'm going to call another student. Bùi Quang Mạnh.
Yes.
Yes. Yes, please answer my questions.
I think I will train the turn W1.
Turn W1. Okay, the turn W1. So why that? For example, if we are talking about the step down transformer, it means that. So why I'm saying a step down transformer? It means that the W1 is connected to the high voltage, okay, and of course W2 is connected to low voltage, okay, because for the step down transformer, it means that the input is normally is connected to the high voltage, and of course for the secondary winding is connected to the low voltage. Okay, and now so you are saying that we have to change the turn number of W1. It means that the voltage level of W1 is very high. Okay, for example, is the 22 kilovolt. Okay, so why that? Can you explain to all of you? To all of us, sorry, to all of us.
If the transformer is step down.
Yes.
Yeah,
step down transformer. Yes. Okay.
I think if it will depend on the kind of transformer. If transformer is step down, I think we should train the turn of W2.
Okay, so few seconds ago, so you said that we need to change the turn number of W1, and now you switch to W2. Okay.
I think we will depend on the kind of the type.
Yes, I'm telling you, we are considering the step down transformer.
Yes.
Step down transformer. Yes. Okay. So we are focusing on the step down transformer, of course. And now, so for example, if this problem we are considering, okay, for the step down transformer, okay, I would like to ask you again, okay, according to you, you need to change the turn number of W2 or W1. You understand my questions or not?
Yes. Yes.
Yes. Okay. Please answer. If you have no answer, I would like to ask another student.
I think I will. I think I will train the turning of W2 because it's a low voltage and. I think it will save for the engineer.
Okay, save for engineer. Okay, it means that so you will change the turn number of winding getting low voltage. Okay,
Yes.
Of course, I would like to ask another student. Okay, so everyone agree completely with the answer of Bùi Quang Mạnh or not? Okay, if you are agree completely with this answer, okay, who? Okay, Đào. Let me check. Đào Huy Hiệu, please answer my questions. Go ahead.
Thầy, em nói tiếng Việt được không ạ?
Yes, because in our class, okay, I think you should try to speak English with Vietnamese, because in our class, there is a student coming from the Sri Lanka. She cannot understand if you speak Vietnamese.
Thì em hơi tệ thì thôi thầy.
Okay, no problem. You should try. Okay, should try and speak slowly. No problem. Okay, no problem.
Because I think we should change W2 because in step down transformer, W2 will have more will get higher value of number
Correct.
y. Number y, so that when we change W2 we will have more choice of we have more choice. We will have many choice of the number of y in of W2. Can you understand my idea?
Okay, so it means that you have the same, of course, you have the same idea with the previous student, but different explained. Okay, different explanation. And I would like to ask another student to see how it's correct.
Em là khi mà em chọn bằng dây 2 đấy, em dây thứ cấp thì do là cái số vòng dây nó lớn nên mà mình có thể chọn được nhiều giá trị để cho nó đưa ra được cái kết quả của U2 nó chính xác nhất.
Yes, I understand. Yes, I understood what was saying. But I mean that okay. So why do you think the number of W2 is bigger than W1? It's because normally you can change. Okay, you can change either W1 or W2. Okay, W1 or W2. The turn of W1 or W2. Okay, and of course, the idea is that so we need to change the turn number of W2. Okay, it means that you have to change the winding getting a low voltage. Okay, low voltage is the same answer as a previous student. Okay, and now maybe I think I should ask. Yes, I should ask another student to see how it's correct or not. Okay, thank you very much. Okay, so even you are trying to speak English and also trying to explain something. Okay, it's no problem. Okay, and who can answer my questions anymore? Who can answer my question anymore? Please go ahead. Please go ahead. Don't hesitate.
Can you repeat the question, please?
It means that up to now you haven't understood my questions. Even there were 2 students answer my question.
I think we should change the W1 because it's the outside of W2.
Okay. So it means that you come back to previous. You come back to the previous slide. Last week we were talking about about the location the location between the primary winding and the secondary winding. Okay, you also remember the location of W1 of the high voltage winding located far from the magnetic circuit. Okay, yes, right. But I think you should explain a little bit about that. Okay, so you know that. So you answer that because of locating, because the W1 is located outside of the the W2. It means that it's very easy for us to change the number term of W1. Okay, and for the first idea is correct. It's correct, and I agree completely with the answer. Okay, and I think you should try. You should try to think another idea. I think it's very, very important. It's very, very important. Yes, all right. The first idea is correct. Of course, we have to change the turn number. The turn, yes, the turn number turn of winding W1 with the high voltage. So why that I would like to explain to all of you, because you know normally for the high voltage, for apply high voltage in the winding, it means that the flowing current in that winding is very low. It's very low. You know expression. It's very easy for you to understand. So for the current S equal to, you can see here, is square of. You can see here and here. It's okay. And for example here, as I said before, and for the primary winding, it's connected to the high voltage because we are considering for the step down voltage. It means that the input voltage is higher than the output voltage. It's higher, okay? It's higher, and sometimes for the input voltage, 22 kilovolt or 35 kilovolts, or even 110 kilovolt, or 220 or 500 kilovolt. And of course, for output voltage, for example, we are using electricity like the 380 volt for three-phase voltage. Okay, of course, for the side you are using a single phase voltage or the phase voltage of 220 volt. Okay, 20 volt. It means that when the output voltage is very low, it means that you can see here. Have a look at this expression. This expression, you can see if the voltage value is very low, it means that the values of the current is very high. It's very high. If very high, you can see if you want to change the turn number of the winding getting very high, current value is very dangerous because you can see. So when the current is very high, it means that we have to produce the point of contact. You know the point of contact. The point of contact. Maybe I say the point of contact here. I'm not sure you understand point of contact. You can see the point of contact here. The point of contact between, because you can see. So when we switch from this level to another level, and the ask between the point of contact is very high, and for that it's very dangerous for the wiring of the transformer. And otherwise it's not so easy for designer and for engineer to produce a point of contact, because for each voltage level we get each point of contact. Okay, and for that, in order to reduce the current values, okay, and by changing the turn number of the wiring getting the high voltage, because when the voltage is very high, it means that the current value is very low. So that's reason why for every transformer, okay, we get two reasons. The first one, because the high voltage wiring is located far from or outside the low voltage wiring, okay, and or far from the magnetic circuit, and it's very easy to change the turn number of that wiring. And the second idea is that when we change the turn number of the wiring getting the high voltage, is mean that the point of contact is very easy to produce. Okay, okay, you should so by keeping in mind these 2 points, okay, so we can repeat this idea in the future. Okay, and of course for this reason you can even maybe I think if you come back to some or more than 10 years ago, I think even 20 years ago, and with my generation, generation. Okay, so we have to use the very old-fashioned transformer. Okay, for each time, if the output voltage is not as a constant, okay, we have to change. We have to change by using some switch mounted on the transformer. Okay, it means that we have to change the turn number of the winding, and of course for the side with the low voltage, with not high voltage. Okay, with not high voltage for that. Okay, and of course we have just talking about the transformation ratio of the transformer. So keeping in mind that this concept is very important, because this one will be appearing on the voltage balance equation and also something else. Okay, and now it's high time for us to talk about the rated parameters of the transformer. Okay, and normally it's before using every electrical machine, not only transformer but also other machines such as the motor or the other electric device. Okay, you should take care of nameplate of the machine. Okay, and because we are talking about the transformer, and for that we have to take care of the nameplate of the transformer. Normally the name for every transformer, even for step down transformer or the step up transformer, and the nameplate mounted on the tank, yes, on the tank of the transformer. Okay, and how things in the nameplate, because through the nameplate of the transformer you can know every rated parameters of the transformer, and such as the voltage, the current, and the power, and no load current, and the condition of transformer, and the no loss and short circuit losses, and something else. So even for the isolation class level, okay, isolation level, and something else. Okay, and for that, and now we are talking about some parameter like a rated voltage and the rated current and the rated powers. Okay, and for the rated voltage, depending on the connection of transformer. A transformer, have a look at the figure on the right hand side of the slide. You can see, for example, if the transformer is the winding of the transformer is connected in a delta connection, okay, in delta connection, or is a star connection here. Okay, and of course in delta connection here, according to you, so whether you can take the phase voltage or not, according to you, for the delta connection here. Have a look at this one. Okay, because have a look at this one. We are talking about the delta connection of the winding of the transformer. Okay, and now, for example, if you want to take the phase voltage, how to do? Phase voltage, how to do? How to do? You know. Please answer my questions. Please answer my questions. The monitor, can you answer my questions? That có đây không? No. Do you understand what I'm asking you? The questions.
I don't understand very much.
You don't understand very much. Okay, it means that you have no answer for my questions. Okay, it's no problem. And for other students who can answer my questions, for example, if you look at the delta connection in the figure, okay, of course, and now if you want to get the phase voltage, how to do? What to do? And from that you can understand that. And for the step down transformer, normally for the high voltage wiring is connected in delta connection, and of course for the low voltage wiring is connected in star connection. So why are the transformer connected like that? Okay, yeah, like that. Yes, please answer my questions. No, you have no idea for these questions. Okay, so I would like to explain to all of you. Have a look at this one. Okay, you can see, and if the wirings of the transformer is connected in delta connection here, it means that we cannot take the phase voltage. Why that? Because we have no neutral point of this one. We have no neutral point of this one. If you want to get a neutral point of this one, of course you have to use another. You have to use another winding, and then we connect that winding in delta. And for that you will get the sub neutral point. That's a sub neutral point of the winding, and from that you will get the phase voltage. Okay, the phase voltage. And of course for the delta connection here, okay, you can get the line to line voltage. So line to line voltage is means that we have to take the voltage between two phases. For example, here we can take the voltage of phase A and phase B, also. Or even you can take for example, here you can get the UAB, okay, UAB, or otherwise you can take the line to line voltage, okay, line to line voltage of phase B and phase C. So it's very easy. Okay, in some textbook, written line to line voltage or the line voltage is the same. It's the same meaning but different coding. The same meaning but different coding. Okay, have a look at delta connection. It's very easy for all of you to imagine what is and where it is, the line to line voltage, and also the phase voltage. Okay, of course in this one, for example, if the delta connection, it means that the phase voltage, you can see the phase voltage, okay, and the phase voltage is equal to, of course you cannot use directly the phase voltage in this diagram, but you can compute, okay, and in this connection, okay, you can compute the phase voltage, but you cannot use directly this voltage level. For example, and now you are sitting at the home, okay, the voltage level of 220, okay, okay, you cannot take directly from this diagram, okay. Of course you can compute, okay, and because for the because why is that? Because there are no neutral point. Okay, you have to produce the neutral point in this diagram in order to get the phase voltage for the electric device at the home. Okay, and how to compute? Okay, you can see, for example, for the delta connection, so you can see the phase voltage is equal to the line voltage. It's the line voltage, and of course for the current is the inversely. Okay, and have a look at on the right hand side of this finger, you can see the star connection, and now we understand very well how to connect the wiring of the transformer in the delta connection or star connection. You know well already, because because I think last 2 weeks I already show you the way of connecting the wiring of the transformer in a star connection or delta connection. Okay, and here you can see we get a neutral point. For example, at the home, if you want to use directly the phase voltage, Of course, it's very easy. You can take the phase A and the neutral point, and also phase B and neutral point, and phase C neutral point also. Okay, that's all. And of course, depending on the star connection, okay, we can get the current values and the voltage value, of course, through the expression of this one. Okay, and here you can see line to line voltage. Okay, line to line voltage here. Okay, and of course, in this one you can take the line to line voltage also. Okay, this one line to line voltage also. Okay, maybe I think I would like to present by using presenter view. I think it's better. And here I would like to show the point laser. Okay, and here's a laser pointer. Okay, and yes, and here. Okay, and of course, and the phase voltage, you know the concept already. Line to line voltage, you know already also. Okay, I would like to turn on my camera. And so sorry to. Okay. Yes, and normally for the unit of each voltage of the winding of each winding, so we get the volt or kilovolt depending on the power capacity of each transformer. Because if the power capacity of the transformer is very big, okay, instead of using the unit like the volt, we can use a kilovolt. Okay, it's nothing special for that. And in the same way for the secondary winding, okay, for secondary winding, secondary power windings, and for the voltage, we can denote a volt or kilovolt. Okay, volt or kilovolt also. And now we are talking about the rated currents. Rated current. Rated is the nameplate of the transformer. Okay, the transformer here. Yes, the primary current is the same way. Have a look at here. For example, if the winding of the transformer is connected in delta connection, you can see the phase current. The phase currents or the line current is equal to phase current because of the connection in delta connection. Okay, in delta connection, and for that we get the like, okay, the line current. The line current is equal to square of √3 multiplied by the phase current here. Okay, and this one, if you look at this one simply, but it's very, very important. It's very, very important because you have to apply this concept and that concept also to solve our problem in the middle exam or the final exam. Okay, so up to now I have seen a lot of students solving the problem wrong way. Okay, because if they don't remember all the theory, even and this concept is very simple. Okay, and of course the unit of primary winding, primary current or the secondary current, okay, is normally in ampere or kiloampere, depending on the values of the current flowing in the winding, and also depending on the load capacity. Because if the load capacity is very big, it means that the current is very high. And for that, instead of using the unit ampere, okay, they can use kiloampere, okay, kiloampere for that. And for the final rate powers, I would like to show you. That is the rate power of the transformer. And of course here, if you look at for the first line of this line, you can see for the for a single phase transformer, we get expression of apparent power here. As normally you can see for the unit of the transformer, they usually use the apparent power instead of using active power or reactive power. Okay, because the unit of this one is kVA, VA or kVA, depending on the power capacity. Okay, and of course for single phase, and the apparent power which can be defined by this expression. Okay, U1 multiplied by I1 and also U2 multiplied by I2 here. Okay, and this one for the single phase. Okay, single phase, and of course the unit of this one, as I said a few seconds ago, the VA or the kVA. Okay, and of course when we are talking about the three-phase transformer, a three-phase transformer, and the expression of three-phase transformer, which can be expressed like this. Okay, you can see here. So the S is equal to square of the square root 3 U1 multiplied by I1, and also here. Okay, and of course I have just introduced you the three main rate parameters of the transformer, and the rate voltage transformer, and the rate current transformer, and also rate power transformer. Okay, and as I said before, in the needle of the transformer, okay, we get a lot of parameters. Okay, from the main parameters such as the current, voltage, and the power. Okay, and of course you can see the insulation level. Okay, insulation level and temperature, and the connection of the winding, and also no load losses and short circuit losses. Okay, and the frequency also. Okay, and up to now we have just finished the second section, general concept of transformer, and now it's high time for us to go to the next section, is the electromagnetic relation in transformer. Okay, yes. So is this so in this part we are talking about the voltage and voltage balance equation, and also magnetomotive force balance equation. For doing that, and the first of all, we need to introduce you about the direction of the current and the voltage. So have a look at the figure. Have a look at the figure on the left-hand side of this slide. You can see, and this figure is stand for the single-phase transformer, consisting of two different winding, W1 and W2 here. Okay, one is connecting the primary winding is connected to the either no voltage or the high voltage, depending on the type of transformer. Okay, and of course the W2 is connected to the load here. Okay, and if you remember the principle of the transformer, it means that for the for example, the W1 is applied by the voltage, the E1. It means that we get the current flowing in the W1. Okay, in the current flowing in W1, we induce the magnetic flux. Induce a variation of magnetic flux through the window of the W1 and W2 here. Okay, and this magnetic flux is called the main magnetic flux. Okay, and in addition, we can see carefully. You can see the B side of the main magnetic flux. We get two different magnetic flux, the phi T1 and phi T2, and the phi T1 and phi T2 are calling the leakage flux. So you can see for the main flux vary very continuously through the window of W1 and W2. So according to the electromagnetic induction law, we can get, so in W1 and W2 we get E1 and E2, because E1 and E2. And of course, for the leakage flux, you can see here the leakage flux phi T1 and phi T2 also induce an electromotive force. Okay, electromagnetic force. And here I think electromagnetic force. Okay, electromagnetic force ET1 and ET2 in W1 and W2 also. Okay, W2 and W1 also. And from that we can get the ET1. Okay, ET1 is the electromagnetics due to the diffusion of the liquid flux phi T1 and phi T2 here. And this expression can be defined by this one. And in the same way, we get the electromagnetic force E2 due to the liquid flux phi T2, which can be defined by this expression also. And L1 is the inductance of W1 and L2 inductance of W2 here. Okay, so keep in mind this concept. Keep in mind this concept. And now so we can write the voltage balance equation by applying the second Kirchhoff to the both side of magnetic circuit showing in the figure a previous slide. Here you can see, yeah, by applying the second Kirchhoff for this magnetic circuit, okay, for the loop 1 and for the loop 2, okay. And for that we can write the voltage balance equation of the primary winding and the secondary winding like this. And of course you can see the E1 due to the main magnetic flux flowing through the window of W1, okay. And of course here for the term, this one is the term is one due to the term this one is the voltage drop on the primary winding. And of course this part belonging to the liquid flux, okay, because the liquid flux also induce electromagnetic force ET1 like this. And also in the same way we get the second voltage, okay, the second voltage balance equation here, okay, here, okay, by on the left hand side of the magnetic circuit we get this one. And normally instead of using the tariff equation, okay, the voltage balance equation are written by the complex number. It means that for the normal letter like this, okay, normal letter like this, we change by the capital letter, you can see here. But of course because on the top of this one we have to, on the hat we have to use a dot like this. Let me come back to here because I already here you can see the dot like this, okay, dot, because and from the normal letter here, okay, we can change from the normal letter to the capital letter with the dot here. It means that because in this one I do a missing here, but you need to correct on the on the slide, okay. So you want with dot here, okay, with dot here, okay. And also, and you can see for the normal E1 we get capital, okay, we have capital E1 and R1 also. And of course for d divided by dt is equal to g omega, okay. You can see g omega, and I1 is we can move so outside bracket like this, okay. And also in the same way we get the E1, yeah, the E1 U2 like this, okay. And of course have a look at this one, we can see the R1 and R2 are the resistance of primary winding and secondary winding as well. And also the L1 and L2 is liquid inductance, okay, of primary and secondary winding respectively, okay. And how about the Z1 and Z2 here, okay. You can see Z1 is equal to R1 plus GX1, and also R2 is equal to R2 plus GX2 here, okay. It's the complex impedance of primary and secondary windings, okay. So keeping in mind the voltage balance equation of the primary and the secondary windings, okay, we can come back to this equation to use in the setup, okay, in the setup voltage and magnetomotive force equation of the transformer, okay. And now let me move on to talk about the magnetomotive force balance equation, okay. And for answer these questions, okay, so first of all, we have to consider two different way. Okay, the first way, we have to consider the output voltage of the transformer is not connected to the load. It means that the primary winding, the secondary winding of the transformer is not is open. So when the secondary winding of the transformer is open or is not connected to the load, it means that the load current is equal to 0. The load current is equal to 0, and at that time, and the primary current is equal to no load current, or otherwise we get the I1 is equal to I0, because I2 is equal to 0 already for the no load. Yes, for the no load. Okay, and for that you can see the magnetomotive force. Magnetomotive force due to, okay, it's generated by the product of I0 and W1. Okay, product of I0 and W1, because the I0 is equal to I1. I1 is equal to I1. Okay, I0 is equal to I1. And the first idea is that, and the second idea. So if the output voltage of the transformer is now connected to the load, it means that the load current will appear. The load current will appear on the secondary winding of the transformer, and at that time, magnetomotive force generated by the both primary and the secondary magnetomotive force. It means that we get I1 multiplied by W1 plus I2 W2 also. Okay, and for this case, it means that the output voltage of the transformer is connected to the load, and the previous case here for the no load. Okay, and we should know that. So if apply voltage in the primary winding of the transformer is a constant. Is a constant for both case, for the no load current or for the load current. It means that the magnetic flux due to the current, okay, due to the no load current or the load current is also constant. This means that the general magnetomotive force is a constant in any state of the load, for the no load or for the load. And from that we get the magnetomotive force balance equation like this. Okay, like this. And for this case, you can see for the no load current here and for the full load current, it means that for an I0 W1 and for the case of the transformer not being connected to the load. Okay, and of course on the right hand side of this expression you can see, and for this case when the transformer is connected to the load. Okay, because the applied voltage for both cases are not changed, or we can say it's a constant, and for that we get the magnetomotive force balance equation, which can be defined like this. Thanks to this expression, and now by dividing on the both sides of this equation by W1, okay, by W1, and we get like this. You can see I0 W1 divided by W1, okay, and I1 W1 divided by W1, and of course we can see and W2 divided by W1 here. Okay, and normally instead of writing like this, okay, and if you come back to previous slide, yes, you can see we get the ratio of the transformer, or we can say the transformation ratio K. So K is equal to W1 divided by W2, and now W2 is divided by W1. We guess is equal to is equal to 1 divided by K here. And for that, instead of writing W2 divided by W1, we can write like K. Okay, and of course we get finally we get the magnetomotive force balance equation is also the current balance equation like this. You can see, and I2 divided by K is equal to I2 time here, okay, with comma, exponent is followed up I2 comma like this. And of course, the I2 time here is the reference current. Of course, for this one, we can discard in the next line, okay? Where the K, yes, you know already, K is the transformation ratio, okay, which can be defined by this one, okay, from previous slide, okay? If you don't remember this concept, you can come back to maybe I think several slide, previous several slide, okay? And once we get three different equations, balance equation. The first one is the voltage balance equation, the primary winding and the secondary winding. And now we get also the current balance equation or the magnetomotive force balance equation. And now we get the set of three balance equations. It's rewritten as, you can see E1, you can see its complex number. As I said before, in the capital number with the dirt, okay, like this, the head of this one, the dirt, okay, and here for the primary winding, and here for the secondary winding of the transformer, and here's the current balance equation, okay, with I2 times, you know, wow, it's the reference current from the secondary winding to the primary winding, okay, and for this concept, for this concept of the reference current here, okay, so we can discuss in the detail in the next slide, okay, for that's why. And now let me move on to next slide to talk about the reference transformer here. For the reference transformer, so you can imagine that in our transformer we get two different winding. We had two different winding, and that's winding, okay, because that's why are not connected together, okay. And let me come back to here. This slide you can see, okay. Just show it quickly, okay. Just show you quickly about that. You can see we get two different the winding, okay.
Excuse
the first
me, teacher.
Yes.
Teacher, still we can see 52 page.
Okay. 52.
I still can see 52 page.
Yes. Okay. Okay. Here. This. Yes. Yes. Do you have questions for this slide?
No, I didn't have questions, but I can see on 52 pages. Still, I can see this.
Okay. Okay.
No,
Okay. Okay.
Teacher, seems like your slideshow doesn't change.
Doesn't change.
Yeah.
52.
It's still at the 52
Yeah.
slide.
Is this okay already or not?
Still saying.
The same. Okay. I don't know why that's 52, because here I think on my side 52. Let me check. Okay, and for this way, it's better for you to see or not, to visualize. Is this okay?
Not yet.
Not yet. Let me share again. Maybe I think. And now, is this okay for you to see the slide 52 or not?
Yeah.
Yes?
Yes.
Okay. Yes. Maybe I think because if we switch from this state to another state, maybe something sometimes there's some problem with the PowerPoint. I don't know why that. Okay. Yes. Are you clear with this slide, or if you have some questions on that, I would like to explain. So if you say it's okay, let me move on to another slide.
It's okay.
Yes, okay, okay, thank you. And for this one, it's okay already. Maybe I think I would like to make a zoom here. Yes, right. Okay, yes, for the set of three balanced equations. Okay, it's written like this. Okay, so keeping in mind the voltage balance equation, the primary winding and also the secondary winding. Okay, and for this equation is very, very important. It's very, very important for all of you, even for set of vector group, and also thanks to this equation you can solve the problem to find how is the values of primary windings, and how is the how is the values of the secondary winding. Okay, and for this slide I would like to say, I'm talking about the reference transformer. Okay, if you come back to the single phase transformer, for example, okay, you can imagine that we get two different winding. We have two different winding. Two different winding, and for example, primary winding and the secondary winding. Yeah, secondary winding, and two winding are not connected together. Okay, and now if you want to get the information, or if you want to get the relation between two winding, okay, between two winding, how to get? Because you can see even we apply the voltage in primary winding, okay, in the secondary winding we get the voltage also thanks to the distribution of magnetic field in the magnetic circuit. Okay, magnetic circuit, and for that the input energy converts from primary winding to the secondary winding. You know well already. And now if you want to solve the magnetic circuit with no information between the primary winding and the secondary winding, even the input energy transform to the output energy. Okay, output energy, but we have no information. And for that, if you want to get the information or relation between two winding, of course we have to do reference transformer. That's what I'm saying. Okay, have a look at this slide. This slide you can see the two winding. Okay, two winding as isolated together or are not connected together. Okay, and now if you want to get the relation as I said before, of course we have to imagine. You have to imagine, or we have to do a conversion from the conversion parameters from the secondary winding to the primary winding. Okay, and conversion parameter like that: the voltage, the current, the electromagnetic force, or resistance, inductance also. Every parameters of secondary windings must convert to the primary winding. It means that you can see normally we get two different voltage level, and in primary windings the voltage in primary winding of 22 kilovolt, for example. Okay, and in the secondary winding, the voltage is equal to, for example, for instance, 0.4 kilovolt with a different voltage level. Okay, and now we have to imagine that we have to connect the secondary winding to the primary winding. For doing that, we have to consider the voltage level of secondary winding is equal to voltage level of primary winding. Okay, so if the voltage level of two different winding is different, it means that we cannot connect together. And now if you want to do conversion parameter from the secondary winding to the primary winding, of course we have to consider the voltage level of secondary winding is equal to the one of the primary winding. It means that 0.4 kilovolt is equal to 22 kilovolt. Okay, 22 kilovolt. And following that, we can solve our problem. Okay, so if we don't do conversion, and for that there are no relation appearing in the voltage balance equation, and for that we cannot solve our problem. Okay, and of course you can see when we do conversion, it means that the reference values are noted with the exponent comma. You can see, for example, U2 E2 belonging to the secondary winding. And now, so after doing conversion, okay, or we can say, because in some textbook written reference transformer or the conversion transformer is the same. It's the same meaning. Okay, so after doing the reference transformer, it means that we can see the parameter change. So E2 with the, you can see, so with the exponent comma here, and U2 here. So you can see I2 here, sorry. So I2 here. If you come back to previous slide, like this, you can see I2 here. You can see, so I2 here, yes, I2 here is equal to I2 divided by K, where K is the transformation ratio, okay? Being equal to W1 divided by W2, okay? Yes, you know well that's concept. You can see, and for this one, okay, after doing conversion or after doing the references, okay, we get the U2 with the exponent comma and I2 with exponent comma, okay. In the same way, we get the resistance, inductance, and also electromagnetic force, okay. And now, okay, and now we do step by step, okay, do step by step for each parameter of the transformer on the secondary side, okay, here. And of course, first of all, we are talking about the reference secondary electromagnetic force and the voltage, okay. In order to do conversion, okay, as I said before, two windings should have the same voltage level, okay, the same voltage level. So is either you can convert from the primary winding to the secondary winding, okay, or from the secondary winding to the primary winding. But in practice, some parameters of the secondary windings will do conversion to the primary winding, okay. And for that here, for example, here you can see, and for the electromagnetic force of secondary winding, and now we transform, now we refer to the primary winding, okay. And for each parameter, after doing conversion, we get the E2 with the exponent comma here, okay. You can see, yes, of course, and this thing we keep the same, okay. And of course, it means that when we do, you can see, for example, E comma 2 here, okay, is must equal to 1 here, like this, okay, like this one, because in our opinion, okay, we have to do conversion, some parameters from secondary winding to the primary winding, and for that we get electromagnetic force of secondary winding like this, okay, must be equal to like this, okay. And for that you can see, and E2 times or E2 with the exponent comma here is equal to this expression, okay. Otherwise we get the parameter before doing conversion, E2 is equal to like this, okay. And now if we take the ratio, of this one to that one, okay, we get, of course, here by transforming a little bit mathematically, so we can get like this expression. So E2 here, E2 time is equal to W1 divided by W2 multiplied by E2, and this one, and this term, you know, this term is equal to transformation ratio of the transformer, you know, from previous slide, okay. K is equal to this one, okay. And up to now you can see, so after doing the conversion, okay, we get E2 time is equal to K multiplied by E2 before doing conversion, okay. It means that, and here the meaning of this expression is that if we want to get the same voltage level from the secondary side to the primary side, of course we have to change the transformer ratio. The transformer ratio is the same theory, okay. And here, okay, you can see here, okay. So keeping in mind this one, okay, and E2 time is equal to K multiplied by E2 before doing conversion, okay. Have a look at, because sometimes they will ask you, and what is the meaning of E2 time here. Of course, you can see, and this one is the reference quantities after doing the conversion. Of course, here for this one, and the parameter here is the parameter before doing the conversion. Okay, and now so we will perform for the reference secondary current to the primary winding. Okay, you can see, and for doing that we have to imagine with the no change of transmission power. Okay, with the no change of transmission power, and for that we get so you can see, and for this term is the energy, the input energy, and here's output energy also. You can see, and we get, it means that, and for this it means that for energy before doing the conversion, okay, must be equal to the term after doing conversion. And for that we get E2 multiplied by I2 is equal to the term after doing conversion, like this. Okay, and from this one it's very easy for us to deduce. So E2 time is equal to this term divided by I2 time is equal to this term divided by E2 time here. And you can see E2 time is equal to this one. And for that we can get the I2 time is equal to I2 divided by K. It's the same thing previous slide we get. And this one is called the reference. It's the reference current. It's a reference current. Okay, from the secondary winding to the primary winding. Okay, and of course, and for this one we call the reference electromagnetic force from the secondary winding to the primary winding. Okay, and now we are talking about the reference primary resistance and inductance. Okay, and for doing that we can imagine that with no change of power loss, it means that before doing conversions, okay, must be the same, must be equal to the term after doing conversion. And for that you can see, because we are talking with the no change of the power losses, and for that we get this term is equal to that term, and this term is mean that before doing conversion and after doing conversion. Okay, because if you want to have the no change of power loss, okay, of course we must get like this. And from this one it's very easy for us to get the reference resistance. Okay, reference resistance equal to this one, and that where the transformer ratio is equal to W1 divided to W2. You know well from previous slide already. Okay, and of course in the same way we can get for the reference inductance. Okay, like this. Okay, nothing special for this. Okay, so finally we will get the set of reference equations. Okay, reference equation like this. Okay, you can see here, and of course, and in this the set of reference equation. Okay, for the primary voltage balance equation we keep the same. Okay, we could keep the same, and we only do conversion from the voltage balance equation of the secondary winding, okay, into the primary winding. And for that you can see something changed in the secondary in the secondary voltage balance equation here. You can see, so for previous equation in the previous slide you can see U2, and now so U2 it changed already. U2 you can see here, so U2 with the epsilon comma. Okay, of course E2 with the epsilon comma, and I2 also. Okay, and by replacing some reference parameter in the previous slide we get the new voltage balance equation here like this. Okay, and of course we can see here, the current balance equation with the reference parameter here. Okay, and of course this set of reference equation you should keep in mind. This one is very, very important. And for this equation, okay, we can build the equivalent magnetic circuit for the transformer, equivalent magnetic circuit for the transformer. Okay, and let me move on to next slide. We are talking about the equivalent magnetic circuit and vector diagram of the transformer. And for this one is very, very important also. And based on the basic equation of the transformer written from the previous slide. Okay, and now we can draw. Okay, we can build. You can build the finger, and we can build the equivalent magnetic circuit. Okay, magnetic circuit for the transformer here. You can see. And let me come back to this slide. Okay, keep in mind these equations. Okay, this equation. Okay, and from this equation, okay, thanks to this we can yes, we can build the equivalent magnetic circuit for that equation also. And thanks to this you can imagine. Of course, if you want to, based on this figure, if you want to write the voltage balance equation and also the current balance equation, is very easy. Okay, and of course in practice, in order to get a simple equivalent magnetic circuit, okay, we can transform from the complicate equivalent magnetic circuit to the simpler magnetic circuit like this. Okay, and of course you can see I0 here. Okay, and I0, and of course for the, have a look at on the left hand side of the figure B. Okay, you can see the, if we take a loop of this one for the second Kirchhoff, okay, we can write the voltage balance equation. Okay, and of course on the other side, okay, it's very easy for us to rewrite the voltage balance equation of the secondary winding. Okay, of course this one. And if you look at this one, you can see some reference parameters, U2 time and R2 times and X2 time. Okay, for the secondary side. Okay, for the secondary side here. Yes, secondary side. Yeah, and of course in practice, you can see the imbalance of magnetic branch here. It means that magnetic branch here are very high in comparison with the others, with the branch of primary winding and the secondary winding. This means that the magnetic current flowing in this branch is very, very low. It's very low, of course. And for in the same case, if we are considering for the motor case, okay, electric motor, and the I0 is very, very big, but for the transformer, I0 is very low. Normally, the I0 of the transformer is equal to from the 2 to 5% of the rate current, like this. Okay, let me write here. I0 in practice, I0 here is equal to maybe, I think, from 1% to 5%. 5% here. I make a bracket like this and rated current. Yes, like this. Okay, multiply. Maybe I think yes, text like this. Okay, and so why do I emphasize this value? Because when you do the middle test or the final test, okay, sometimes this expression appear on the questions, and for that you can see, okay, and how is the values of I0 and also the rated current. Of course, the rated current you have to compute thanks to the formulation. Okay, yes, for this, and of course you can see here because of the low current value here, and for that this branch, okay, because this branch sometimes is which can be neglected, and for that, from this diagram we can get the shorter diagram. Okay, the shorter diagram like this. Thanks to this diagram, Okay, thanks to this equivalent magnetic circuit, it's very easy for you to solve this, to solve the equation in this equivalent magnetic circuit. Okay, and of course you can see R end or X end or RPT is the resistance of the load and inductance of the load, and of course Rn is equal to R1 plus R2, and also here, and R1 is the resistance of primary winding, and R2 is the resistance of the secondary winding, and in the same way we get the values of X1 and X2 also. Okay, yes, for this, and that is the we have just talking about the equivalent magnetic circuit, and now it's high time for us to move on to the vector group of the transformer, vector diagrams, of the transformer. The vector diagram of the transformer is very important also. And thanks to the vector diagram of the transformer, you can see, you can guess the transformer is connecting to the inductive load or the capacitive load. Okay, because normally you can see the transformer. The transformer is connected. Okay, the transformer is connecting to the load, but you don't know because, for example, you don't know, and the load is inductive load or the capacitive load or resistive load. Okay, and of course, for example, here, if you look at this slide, okay, this slide, it's very easy for you to talk, to guess. Okay, and of course, because I already show you inductive load here. Okay, it's very easy for you. Okay, yes, here the figure, because the vector diagram here is showing the transformer is connecting to the inductive load, and of course for this case is connecting to the capacitive load. Of course, in the middle exam or the final exam, okay, I delete. Okay, I remove this one. Yes, because for example, I remove like this one, okay, because, and then I will show you the question like this, and then I will ask you, okay, and thanks to this figure, for example, on the left hand side of the slide, and can you please tell me that the transformer is connecting to the inductive load or capacitive load or resistive load? Okay, and of course, if you understand very well the theory, of course, is very easy for you to select the best answer right away. Okay, right away. If you don't know, if you don't understand the theory, okay, and otherwise, if you are not in this class today, okay, so I think you don't know how to answer the questions, even the question. Okay, I'm not sure that for the final exam. So at that time you will get offline course or you are still online course. So I think for the middle for the final exam. Okay, of course for the student living in Sri Lanka. So if she doesn't get a condition to come back to Vietnam, maybe I think at that time I will organize online exam for her. Okay, organize an online exam for her. We will see.
No, sir, I'm in Vietnam now.
Ah, already?
Yeah, I come back.
Come back. So when?
March. In March.
In March.
Yeah.
Okay. I don't know. I think because in my mind I think you are still living in Sri Lanka, but now okay you are already in Vietnam. Okay, there's some so how are things? Because and now you know the COVID is very complicated in Vietnam. Okay, how are things with you? Everything is okay, and you will. Do you have some problem with you or not?
Yeah, I have faced some problem, but now I'm okay. Actually, after I come back to Vietnam, when I was at the hotel quarantine period, they found me as a COVID positive, and I hospitalized. And I was, so yeah, it's okay.
Now, yes, okay. So I think if you get some problem, if you have some trouble with with the living, so please ask the student, ask the friend or as a teacher. Maybe I think Vietnamese will support you. I think.
Yeah, thank you very much.
If you have some problem. Okay.
Yeah, already the university
Yes,
support
I know.
me a lot. Yeah.
Yes. Okay. Thank you. Yes. Yes. And now it's high time for me to teach you, to show you the way of drawing, vector diagram of the transformer. Okay, how to draw. And the question is asked, how to draw. Okay, and for doing that, okay, and now for example, we start. Okay, we start doing with the case of inductive load on the left hand side of this line. Okay, left hand side of this line here. Okay, and for doing that, okay, we have to base on the voltage balance equation and also the current balance equation. Okay, you can forget everything. Okay, you can forget everything in everything appearing in this vector diagram. Okay, the first of all, okay, you can see for the transformer. Okay, for the transformer, it's not connected to the load. Okay, when we apply the voltage, okay, when we apply the voltage in the primary winding, okay, of course for the output voltage for the secondary winding is not connected to the load. Okay, of course even there are no the low load current flowing in the secondary winding of the transformer, but in the secondary winding still get electromagnetic force E2, okay, electromagnetic E2, and also in the W1 we get electromagnetic force in W1. Okay, and you can see in order to produce a magnetic flux flowing in the magnetic circuit, okay, we get I0 here. You can see I0 here. Okay, because when the secondary winding is not connected to the load, it means that we get the I1. Okay, we get the I1 is equal to I0. Okay, I1 is equal to I0. Okay, you can see, and the magnetic field due to the distribution of the current flowing in the magnetic circuit, it means that the phi, okay, magnetic flux denoted by phi is a phase delay by I0 with the alpha here. So, okay, phase delay, okay, alpha here. Okay, and of course you can see, and of course for the phi, and now if we connect, so and now if the connect the secondary winding to the load, it means that we get, okay, it means that we get the current flowing in the load. Okay, so before doing that, you can see, as I said before, and when we get a magnetic flux flowing in the magnetic circuit, it means that in the W1, or in the primary winding and the secondary windings appearing electromagnetic force E1 and E2. Okay, and E1 and E2. You can see the E2 is E2, as I said before, E2 is equal to E1. If you come back to this one, you can see E2 is equal to E1, and for that in here we can see and E2 time here. Maybe I think I did a missing, so E2 time here. Okay, and you can see, and here so E2 time here. Okay, E2 time here, and now of course so E2 time is also at a phase delays by phi with the 90 degree, because you can see the E is equal to minus W1 or W2 d phi divided by dt. Okay, and for that the electromagnetic force of the secondary winding is phase delays by phi here. Okay, and of course we get here, maybe I think, yeah, E1 is equal to here, maybe to time here is equal to E1. This, okay, is equal to E1, is 1. And now, okay, and keep in mind this one, okay, and now we allow the secondary winding of the transformer to connect to the load, for example, with the inductive load. With inductive load, okay, with inductive load, it means that, okay, it means that we get the current flowing in the inductive load because of the inductive load, and for that, the current flowing inductive load is also get a phase delay by the electromagnetic force E2, and for that we get, you can see I2 here. I2 is always get a phase delay by the E2 here, and we get, you can see the phase angle between I2 and E2 here, okay, I2 and E2 here, okay, and we get, and you can see here, and of course, and here you can see the I2, the direction of I2 here, and of course, if we want to get, and here is I0, and of course, if we take inversely direction of this one, we get the direction of I2 here with minus here. Okay, of course, here maybe I think we must write it parallel. Okay, but the direction here, the inverse direction here. Okay, and of course we get the I0 here, and of course here we get the minus I2 here, because here we get I2, of course, is the same. Is the same because it's the same line but inverse direction. Okay, inverse direction. We get I minus I2 here, and I0 and minus I2. Of course, we get I1 here. Okay, so I1 is equal to I0 plus minus I2 here. If you come back to the equation of, okay, the current balance equation, we get exactly, okay, exactly here. Of course, when we get I1 here, of course, for beginning we get a phi I0 and I minus I2 also, and I1 here. And now if you come back to the voltage balance equation of the primary winding, as primary winding up here, you can see primary winding here. Primary, you can see I1, E1 is equal to minus E1 plus I1 R1 plus Z I1 X1. Okay, you can see here. And of course, for the previous time, you can see we get the I2 time is equal to I1. It means that I1 is equal to I2 time here, and of course inverse direction, we get minus I1 here. Okay, minus I1 here. Okay, minus I1 here, and now minus I1 here, and now you can see E1 is equal to minus I1 plus I1 R1 plus Gx1 I1. Okay, you can see here the direction of I1, and now we get already I1 here. Okay, so E1 is equal to minus I1, E1 here. Okay, and plus I1 R1. Okay, you can see the portion. Okay, the portion here. This portion must be parallel. Okay, must be parallel with this one, and this portion is R1 I1. Okay, we get E1, okay, plus minus E1 plus R1 E1 here, and also plus G X1 I1. You can see G X1 I1 must be perpendicular to the R1 I1. For that we get here. This one is the angle is the 90 degree. Okay, it's 90 degree. You can see here. Okay, and finally we get, and finally, of course, if you want to get the product of Z1 I1, of course you can see as this. Okay, and this as this is the I1 Z1. Okay, and finally we get the voltage, the I1 of the primary windings is equal to, you can see here, if we take the vector like this, okay, vector like this, we get E1 is equal to minus E1 is equal to minus E1 plus R1 I1 plus G X1 I1 here. Okay, we get the voltage balance equation of primary winding. Okay, and of course for the current balance equation we got already. From here you can see the I1 is equal to I0 plus minus here. Okay, and now how to define, the voltage balance equation of secondary winding. Okay, it's very easy. It's very easy. Of course, based on the voltage balance equation of secondary winding. Okay, let me come back to this slide. You can see, and U2 is equal to E2 time. Okay, plus this term and plus that term. Okay, and of course, up to now it's very easy. You can see here E1 is equal to E2 time here, and the direction of I2 we know already. Okay, we know already here. Okay, of course, and for this part you can see, so U2, okay, U2 is the equal to E2 here, plus minus this one, plus minus this one. Okay, and of course, and thanks to this vector diagram, okay, what do we need to do? What do we need to know? Sorry, what do we need to know about this meaning of this one? Okay, this meaning of this one. You can see. So you can see here. So U2, okay, U2 is the values of E2 is smaller than the values of E2 here. You can see, because E1 is equal to U2 here. And if you look at this one, you can see the vector. Okay, the vector of U2 is smaller. It's smaller than the vector, the values of E2 here. Okay, so why that? Because you can see, so when the transformer is normally, so if the transformer, I would like to explain something to all of you, the meaning of the vector diagram of this transformer. Because when the transformer is connected to the load, okay, with the inductive load, okay, normally, so before connecting to the inductive load, the voltage value of secondary winding, for example, is equal to 400 voltage. Okay, 400 volt. Okay, 400 volt. And now, after connecting to the inductive load, the voltage value is not equal to 400 voltage. If you look at this one, you can see here is the load, inductive load connected to the transformer, to the secondary winding of the transformer. You can see here, yes, you can see here. Because of this load, this type of load, leading to the lower voltage in comparison the values of before. Okay, you can see here. Okay, and I said few seconds ago, for the beginning, okay, let's say again, for beginnings, U2, you can see, for beginnings, for example, U2 time here. Okay, let me check here, time is equal to 400 volt. Okay, yes, and now, and here's for before connecting to the inductive load, for example, here. Okay, we get this one. And now after doing, okay, after connecting, for example, after connecting to the here, okay, and the values and the voltage value is, for example, is equal to for example 350 volt, 50 volt. Okay, 50 volt. Okay, and for that you can see, and before here, maybe I think like this, and I said before time. Okay, here you can see there. And for the low load, so if you remember last time, okay, when I teach you for the electromagnetic induction, okay, so if the output of the conducting bar, for example, or the secondary winding of the transformer are not connected to the load, it means that electromagnetic force value is equal to voltage value. Okay, and after connecting with the load, it means that we have the voltage drop on the load, and for that E2 is different from the U2. So U2 is only equal to U2 if the drop voltage in the load is neglected. Of course, for this one, okay, and the drop voltage cannot neglect it, and for that we have to consider that one also. Okay, and you can see here the voltage now. Okay, after connecting to the inductive load, you can see the voltage like this. Okay, and of course, because of the inductive load, okay, and the voltage value on the secondary winding of the transformer is not the same values before. The same value before, and for that, if you look at, okay, because if you look at the values, if you look at the value of the voltage of the secondary winding in the vector diagram, you can see here. Okay, so where we get the E2 here. Okay, and of course, if you come back to the secondary, if you come back to the second vector group of the transformer on the right hand side of this slide, you can see for the capacitive load. Okay, we can draw in the same way. We can draw in the same way, but you need to take care of direction. You need to take care of direction of the load current flowing in the secondary winding, because for the previous case you can see the direction of the load current like this, but for this case the direction of the load current like this, because you can see for the capacitive load and the current and the load current that's a phase leading by the voltage. Okay, and of course for this case and this case and the load current gets a phase delay by the voltage. Okay, for the inductive load, you know, because for this one and for the theory you already studied in physics. Okay, because for that I don't have to repeat. Okay, and here you can see, if you look at this vector diagram of the transformer, okay, you can see for the inductive load and the values of the voltage is smaller than electromagnetic force. And of course, for this case, you can see when for the capacitive load and the values of the voltage of the secondary winding is bigger, is greater than E2 here. Yeah, it's greater than E2 here. You can see, greater than E2 here. Okay, because of the, you can see, because of the load current at the phase leading by the voltage, and of course this one here. And thanks to that, you can see, and normally for the transformer, so when connect to the, so when it's connected to the inductive load, and we make the lower voltage of the secondary winding, and for that we also put some load level of the capacitive load in order to increase the output voltage of the transformer. And for that one, we have to make a controller unit, and sometimes we have to put capacitive load, and sometimes we have to put inductive load, because if the transformer is connected to inductive load and the output voltage of the transformer is lower than before, of course, and for that time, if we want to increase the output voltage of transformer, okay, by putting the capacitive load like this, you can see, okay, in order to get the values, expected value. Okay, for example, here, let me say again, if you want to, for example, the transformer is supplying for the building, for example, the building, the building for the lighting, for the electric device in the office, for example. Okay, and now if the engineer start with the water pumping, with the water pumping, because the water pumping is inductive load. Okay, and at that time it will make the output voltage of the transformer is not the same value before. Okay, and now for example, from the 400 voltage, okay, down to the 350 volt, and for this, okay, for this value, okay, it cannot be suitable for the electrical device in the office, for example, for the computer or for printer, for everything, for other things also. Okay, and for because for this electric values, okay, they only only operate with the 300 with the voltage of 380 volt. Okay, and now if you want to increase, of course, you can change by putting a little bit the capacity plot in order to increase the values of the voltage here. Okay, and just to show you something in practice. Okay, and of course you can see, have a look at this one. If we come back to the middle test or the final test, okay, so they will give you the question like this. Okay, and of course because for the middle test and the final test, I will give for each student. For each student get maybe I think 40 questions or 50 questions for the final test. Okay, and the questions are different together. Okay, they're different. It's not the same together, different each other. Okay, and for that, for example, for student A, okay, you get a question like this. Of course, without showing you the inductive load, and then they will ask you. And if you look at the figure like this, you can guess, you can think the transformer is connecting to the inductive load or capacitive load or resistive load or the mixed load. Okay, and of course the answer A, B, C, D. Okay, they already gave you the answer. Of course, if you understand very well the theory, okay, it's very easy for you to select the best answer right away. Okay, even for the for this also. Okay, maybe I think it's high time for us to to get 10 minutes for the time break. Okay, or time break. Okay, we'll come back to our lecture in 10 minutes. Okay, I think yes, in 10 minutes. Okay, is this okay?
Yes.
Nghỉ tí các em nhá. Okay. 10 minutes for time break. Okay, so let's come back to our lecture slide. Okay, and for this slide, we're talking, yes, for this slide, talking about the diagram of the transformer. I would like all of you to understand. So why do you have to, yes, thanks to the vector diagram, you can guess, and the transformer is connected to the inductive load or the capacitive load. Okay, and so this one. For example, if the question is that if they ask you when the transformer is connected to the inductive load, it will make the lower voltage. And now if we want to get a higher voltage without changing the turn number of the winding, okay, and how to do? Yes, of course, you know, wow, we have to put a little bit about the capacitive load, and of course, as the same questions before, when the output voltage of the transformer is changed, of course, without changing the type load, of course. And now if you want to get the output voltage of the transformer as a constant, okay, how to do? And of course, as I explained before, of course, we have to change the turn number of the winding for the high voltage winding. So why that is the reason, you know, wow, already. Yes, because, and for that it's very easy, because of the material made the point of contact between the point to point of the, yes, of the winding, and also, and for, because the current value is very low, and for that it's very easy to produce a point of contact. And otherwise, with the high voltage winding is located outside of the primary of the low voltage winding, and for that it also is very easy for us to change, and for engineer, for operator to change the voltage level for each time. Okay, and now it's high time for us to discuss a little bit about the experiment of the transformers, of course. And this part is it's a responsibility of the ladies who will show you how to do experiments, as a laboratory. Maybe I think for this semester, I'm not sure that you will do the experiment with the very new equipment, or still do experiment with the old equipment, because now you know we have the side project. We bought a lot of, side project support of to bought a lot of to buy a lot of new equipment, and for the electrical machine, the transformer and the motor and something else. Maybe I think for the monitor, you should contact the ladies who will show you, who will help you to complete the experiment. Okay, and of course for this chapter, I would like to show you quickly about the experiment of the transformer. In order, and for that, it's all of you will be familiar with the concept of experiment of the transformer. Okay, so have a look at this slide. So I will show you two different way of doing experiment. And the first one, you can do the experiment with the no with the no load of the transformer, or otherwise we can do with the open test, with open circuit test. It means that the output voltage of the transformer is not connected to the load. Okay, and the first case open circuit test. Okay, and in order to be simple, okay, we need to consider for the single phase of the transformer. Okay, you can have a look at this this diagram quickly. You can see with a single phase. Okay, for beginning, you can see here for the input. For this one is for example with a primary winding. Okay, primary winding, and here with a secondary winding. Okay, of course. For example, if this transformer is a step-down transformer, okay, step-down transformer, and for the input, maybe 6 kilovolt or even 380 volt, okay, and output is 220 volt. Of course, for the volt, okay, for example, like this. Of course, in order to, as for the first step, I'm saying is open test. Okay, it's open circuit test. It means that for output here is not connected to the load. You know well this concept already. And now if you want to measure, if you want to measure input, if you want to measure input current, of course you have to connect the ampere met. Okay, ampere met in this diagram in series. Okay, as I said before, for if you want to measure current, okay, of course for the low current, as for the low current values, okay, of course we can measure directly without using the current transformer. Okay, and of course if we get the diagram with very high current, okay, of course for the ampere meter, so we cannot use directly ampere meter to measure the values current for that diagram. So why that at that time we have to use a current transformer as I teach you before. Okay, in order to transform from very high current value to very low current value with standard being 1 ampere or 5 ampere. Okay, I said before. Okay, and here you can see, of course, and the values current, we can use ampere met. Okay, ampere met here to see how it the input values current for the transformer. And also you can see if you want to measure to see exactly the values of input of the source, value of the source of the force before connecting to the primary winding of the transformer. Okay, you can install the voltmeter, okay, by connecting with this line in parallel. Okay, and like you can come back to the previous slide. Maybe I think from the beginning, last week we were talking about that. We were talking about that because for the voltage transformer, if we want to measure, the voltage with a very high voltage. Okay, we cannot measure directly by using the voltmeter. Okay, of course we have to measure through or via the voltage transformer. Okay, and of course in the laboratory in our university, of course, maybe I think if you go there, you can see the voltmeter can measure directly without using voltage transformer. Normally for the voltage transformer, we can use for the high voltage level from the 22 kilovolt to the 500 kilovolt. Okay, of course, because in the laboratory we are using the low voltage system, so that's why you can measure directly. Okay, and here, and of course, how about the wattmeter? Wattmeter to measure the no load current and no load losses in the transformer due to the variation of magnetic flux in the magnetic circuit. Because you can see, so when we get, if you remember the theory, when we get the variation of magnetic flux in the magnetic circuit, we induce the eddy current distribution. Okay, or in English we call the eddy current distribution, but in French language we call the Foucault current. Okay, Foucault current. In the electrical machine, the Foucault current is not very nice for our electrical machine, or eddy current is not very nice for us. We have to think many ways of reducing the eddy current in electrical machine, not only transformer but also other electrical device. But in other application, for example, if you come back to our home, we can see the induction machine. You can see induction. Magnetic induction, magnetic induction. Okay, based on the eddy current variation. Okay, they can produce a magnetic induction machine. Okay, magnetic machine. Okay, you understand what I'm saying or not? Maybe I think you should you should read some textbook or go to internet. You can see what is effective of eddy current, and also we can say what is the advantages of eddy current distribution or the disadvantages of eddy current distribution. Okay, and here is to measure no load. Okay, to measure no load losses of the transformer due to the variation of the variation of magnetic circuit of the transformer. Okay, and here because we are doing open circuit test, and for that here we also connect the ammeter in the output voltage of the transformer to measure, okay, to measure the voltage value here. For example, here if we set for the beginning and the output voltage of the transformer of 220 volt, of course here we can see, and then if output of this one is not equal 220 volt, of course we have to change, okay, we have to change the number turn, okay, the turn number of the winding in order to get the fixed voltage here, okay, the fixed voltage here. And of course when you go to the laboratory, okay, you have to know the way of connecting the apparatus, some equipment like this, ampere and voltmeter and wattmeter, how to connect them to the circuit diagram, okay. Yeah, circuit diagram, you have to know well about that. And of course the ladies and the teacher, the staff, okay, the staff they will she will help you to do that, okay. And after doing experiment, okay, you will define, okay, you will define the, for example, the ratio of the transformer. And how to define the ratio of transformer? For doing that, you have to define, you have to determine the number, maybe I think the primary voltage value and secondary voltage value, and for this you can see. And also you can see, and from that, thanks to this one, you can measure the no load current, okay, by using this expression, okay, and percentage like this. And as I said before, normally the values of the no load current in percentage is equal to 1 to 5, but in practice sometimes in 10% of the rated current. But I think it's maximum 5%. It's maximum 5%, because nowadays a lot of materials to reduce eddy current losses, okay. And for that, when we apply a very new material to produce a transformer, and for that the losses in transformer is very low, and for that the efficiency of the transformer is higher, okay. And thanks to that, you can see the values of low load current is also lower than the transformer made by the old materials, okay, this one. And of course thanks to these experiments of the transformer, we can define, okay, we can define the low loss power losses and the resistance of the transformer. You can see, have a look at this one. P0 is equal to square of I0 here, okay, measures from the magnetic circuit, okay. And when we know the P0, okay, and also we get the resistance of this one by this, and finally we can get the no load impedance and inductance, okay, inductance of this circuit. And you can see the Z0 is equal to this one divided by this one. And once we get the Z0, and also we get R0 here, resistance, okay, of course it's very convenient to deduce the inductance, okay, inductance, okay, is equal to square of root like this, okay. And also how to define the no load power factor, and this part is very important also, okay, no load factor, okay, as normally in Vietnamese they call the cos phi, okay, the cos phi, even in English cos phi also, okay. And of course when the transformer is not connected to the load, it means that the output of the transformer is open, and the values of the power factor is very small. It's very small. And so that's why in practice, and for the operator, even for EVN company, okay, they don't allow operator, okay, they don't allow operator, and they don't allow the transformer, okay, to work with no load, because when the transformer is connected when the transformer is working with the no load, it means that the cos phi of that transformer is very low. When the cos phi is very low, it means that the reactive power, the machine is always transfer reactive power without active power, and otherwise, and the current flowing in the winding in the transmission line of the electrical system is very high, because you can see, if you look at this expression, okay, we can say the current is equal to P0 divided by cos phi multiplied by I1, U1 here, okay? When the cos phi is very low, it means that the values of the current is very high, and it's very high, and you can see, and if we fix the cross section of the cable, as a cable for the designer, okay, and now if the current of the cable is higher than before, it's very dangerous for the cable. And at that time, the temperature of the cable is very high, and will be destroyed also. Okay, and otherwise, when the cos phi is very low, it means that the active power of the transformer is very low also, because P is equal to square of root 3 multiplied by the voltage, the cos phi, okay, the current, okay, and now the cos phi is lower. It means that the active power is low. Okay. On the other hand, when the cos phi is low, it means that the psi phi is higher. So why is that? Because we get the square of cos phi plus square of psi phi is equal to 1. Is equal to 1. Okay, you know that expression. Maybe I think the square, I think is square of phi here, phi here plus cos phi. Maybe I think here I need to use like this. Is better for you to understand. Okay, cos, yes, it's plus phi. You can say is equal to 1. Here in mathematically, okay, we can do like this. And when cos phi is low, okay, it means that the sin phi is high. Okay, when the sin phi, okay, when the psi phi is high, it means that the reactive power of the transformer is high also. Reactive transformer is high also, and we get, if you see the square of root, maybe I think I would like to here I would like to show you quickly like this. So quickly like this, you can see here square of, maybe I think I would like to this one here, or otherwise, yes, okay, it's P plus P here plus Q here, okay, you can see, you can see. So if you can say, so if the if Q, okay, if you can see, if the cos phi is low, it means that the psi phi is higher, and for that, in the transmission line, is only transfer, transfer reactive power without active power, because at that time you can see, in order to keep the apparent power as a constant, when the active power is low, okay, it's low, it means that the reactive power must be higher in order to give the S, okay, to give S as a constant, okay, as a constant. You can see the active power is very useful for us to use, and reactive power is not very useful. Okay, so that's why in practice they have to think many ways to increase the cos phi of the transformer. Okay, and sometimes you can see, so if the cos phi of the transformer is very low, even we don't use electric device, but at the end of each month we still pay money for that. Okay, money for that. That's why. Okay, let me talk about the, yes, for the, and this one is for the open circuit test. Okay, and of course for next slide we are talking about the short circuit test. So short circuit test, it means that you can see the output wiring is the output wiring of the transformer. Okay, is connected together. It's connected together here. Okay, connected together, and then for this one, of course for this one we have to use the change source. Okay, it means that we have to use the electric device which can be changed the input voltage of the transformer. Okay, and that's called the auto transformer. Auto transformer. It means that you can see the input, the you want apply directly to auto transformer here, and the output of this machine is connected directly to the experiment transformer here. And then if we change the short, it means that the output of the auto transformer is changed also, and for that we will get adapt the suitable input of this transformer. Okay, because when the output of the wiring, the output of the transformer is connected together. Okay, and in the machine the current is very high. It's very high, and for that, if we want to get the current values in the transformer is equal to the rated current, and of course we have to reduce applied voltage. We reduce applied voltage by using the auto transformer. And this very clear. When you go to the laboratory, you can imagine. Okay, you can see. Okay, we have to use the auto transformer to change the input voltage of experiment transformer. Okay, and here, because you can see here experiment transformer and here auto transformer to change the input value of this one. Because if we don't get this one, you can see the input of this one is connected directly to electrical system of our university of the 380 voltage. Okay, if we keep the same 380 voltage by connecting output, by connecting output voltage of transformer, the current in this transformer is very, very high. It will be destroy the wiring of the transformer right away. And for that, if we want to keep, it's even when connecting the wiring of the transformer together by keeping the value short current. Okay, because the short circuit current is equal to the red. The values of the short circuit current is equal to the values of the red current. Okay, by reducing input voltage of this wiring. Okay, and from this experiment, of course, I would like to introduce you quickly, because I'm not a staff. I'm not staff to guide you how to do experiment. Okay, I would like to show you quickly in theory, and for that you can define some parameters like the short circuit current and short circuit voltage, and also short circuit the power of the transformer. And from that, it's very easy for us to define some parameters Z and Xn and Rn also here. Okay, and for that you can define the short circuit voltage test. Okay, short circuit voltage is equal to this expression, and also short circuit voltage test for the active component and reactive component also. Yes, and finally we can get the short circuit power factor here, defined by this one. Okay, and of course I would like all of you to remember on this. Okay, this expression here. Okay, this expression here, and when you come back to get applied course and also to do the experiment, okay, you can know how to connect the apparatus or the equipment. Okay, equipment to the diagram. Okay, don't make a mistake for that. Okay, maybe I think it's high time for us to stop talking here, and next week we continue to talk about the operating mode of the transformer. Okay, and see you next week. Yes?
Yeah.
Okay.
Yes.
Okay.
Goodbye, teacher.
Okay, let me
Goodbye,
stop
sir.
talking here. Goodbye. See you next week.
Goodbye, teacher.